Emission spectra help us understand how atoms produce light. Electromagnetic radiation includes radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. As wavelength becomes shorter, frequency and energy become higher. Visible light is only a small part of the electromagnetic spectrum. White light contains all visible colors. When white light passes through a prism, it forms a continuous spectrum. A continuous spectrum has all colors with no gaps. A line spectrum is different. It only shows bright lines at specific wavelengths. Each element has its own unique line spectrum. This is why line spectra can be used to identify elements. Line spectra form because electrons can only exist in fixed energy levels. When an electron absorbs energy, it moves to a higher energy level. When the electron falls back down to a lower energy level, it emits light. The energy of the emitted light depends on the difference between the two energy levels. In hydrogen, different electron transitions create different series of spectral lines. Transitions ending at the first energy level form the Lyman series. Transitions ending at the second energy level form the Balmer series, which is visible light. Transitions ending at the third energy level form the Paschen series, which is infrared. So, emission spectra are produced when excited electrons fall to lower energy levels and release energy as light. Electron configurations describe how electrons are arranged in an atom. First, electrons are arranged in energy levels, also called shells. These shells are numbered 1, 2, 3, and 4. Inside each shell, there are sublevels. The sublevels are S, P, D, and F. Each sublevel can hold a maximum number of electrons. The S sublevel holds 2 electrons. The P sublevel holds 6 electrons. The D sublevel holds 10 electrons. And the F sublevel holds 14 electrons. Each shell also has a maximum capacity. Shell 1 can hold 2 electrons. Shell 2 can hold 8 electrons. Shell 3 can hold 18 electrons. And shell 4 can hold 32 electrons. This follows the rule. Maximum electrons in a shell equals 2n squared. Now let's look at the relative energy order. Electrons fill lower energy orbitals before higher energy orbitals. So the general order begins like this. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p. Notice that 4s is lower in energy than 3d, so 4s fills first. There are 3 important rules for electron configurations. The first is the Aufbau principle. This means electrons fill the lowest energy orbitals first. The second is the Pauli exclusion principle. Each orbital can hold a maximum of 2 electrons and they must have opposite spins. The third is Hund's rule. When electrons enter orbitals of equal energy, they fill them singly first before pairing up. Now let's look at the shapes of orbitals. The s orbital is spherical. The p orbitals are dumbbell shaped. There are 3 p orbitals, px, py, and pz. They point in different directions in space. An orbital is simply a region where there is a high probability of finding an electron. So the key ideas are these. Shells are numbered 1, 2, 3, and 4. Sublevels are S, P, D, and F. Electrons fill lower energy orbitals first. The maximum numbers are 2, 6, 10, and 14 for S, P, D, and F. And within the same sublevel, electrons spread out before pairing. To write an electron configuration, electrons are placed into orbitals in order of increasing energy. The filling order shown here is 1s, 2s, 2p, 3s, 3p, 4s, 3d, and 4p. So we start at 1s, fill it completely, and then move to the next orbital in the sequence. Now let's look at some examples. Hydrogen has atomic number 1, so its electron configuration is 1s1. Helium has atomic number 2, so its configuration is 1s2. Lithium is 1s22s1. Carbon is 1s22s22p2. Oxygen is 1s22s22p4. Sodium is 1s22s22p63s1. Chlorine is 1s22s22p63s23p5. Calcium is 1s22s22p63s23p64s2. For transition metals, we often use the noble gas shortcut. Chromium is written as argon 3d54s1. Iron is argon 3d64s2, and copper is argon 3d104s1. Now let's look at the orbital box diagrams. For oxygen, the configuration is 1s22s22p4. The 1s orbital has 2 paired electrons, and the 2s orbital also has 2 paired electrons. In the 2p sublevel, electrons spread out first, and then 1 pair forms. This follows Hund's rule. For iron, the configuration is argon 3d64s2. The 4s orbital contains 2 electrons, and the 3d sublevel contains 6 electrons. For chromium, the configuration is argon 3d54s1. Instead of 3d44s2, chromium is more stable as 3d54s1 because a half-filled d sublevel is especially stable. This leads to the common exceptions. Chromium and copper are common exceptions to the normal filling pattern. That is because half-filled or fully filled d sublevels are especially stable. One more important note. For transition metals, when ions form, electrons are removed from 4s before 3d. So the key idea is simple. Electron configurations show how electrons are arranged in shells, sublevels, and orbitals. Ionization energy is the energy needed to remove an electron from a gaseous atom. More specifically, the first ionization energy is the energy needed to remove 1 electron from each atom in 1 mole of gaseous atoms. It is measured in kilojoules per mole. Across a period, from left to right, first ionization energy generally increases. This is because the nuclear charge increases, so the electrons are attracted more strongly to the nucleus. Down a group, first ionization energy generally decreases. This is because the outer electron is farther from the nucleus, and there is more shielding from inner electrons. On the graph, the highest points are the noble gases, such as helium, neon, and argon. They have full outer shells, so their electrons are difficult to remove. But there are some important exceptions. From beryllium to boron, ionization energy drops. This is because boron's outer electron is in a higher energy 2p sublevel, so it is easier to remove than beryllium's 2s electron. From nitrogen to oxygen, ionization energy also drops. Oxygen has 1 pair of electrons in a 2p orbital. The repulsion between these paired electrons makes 1 electron easier to remove. Nitrogen is more stable because its 3 2p electrons are unpaired. Now move to successive ionization energies. Each successive ionization energy is larger than the one before it. This is because after each electron is removed, the remaining electrons are held more strongly by the positive nucleus. A large jump in successive ionization energies shows that an electron is being removed from a new inner shell. For example, potassium has 1 outer electron. After this first electron is removed, the next electron must come from an inner shell closer to the nucleus. That is why there is a very large jump after the first ionization energy. Smaller irregularities in the graph show that electrons are arranged in different sublevels such as S, P, D, and F. So the main idea here is successive ionization energies give evidence for shells and sublevels in atoms. Now move to the right side, hydrogen and ionization energy. In the hydrogen emission spectrum, the lines get closer and closer together. The point where the lines converge is called the convergence limit. For hydrogen, this limit corresponds to an electron transition down to n equals 1, the ground state. The energy of a photon at the convergence limit is equal to the first ionization energy of hydrogen. We use 2 key equations. C equals lambda times frequency and E equals h times frequency. For hydrogen, the ultraviolet convergence limit has a wavelength of 91.2 nanometers. Using the equation E equals hc over lambda, the energy per photon is 2.18 times 10 to the minus 18 joules. Then we multiply by Avogadro's constant to get the energy per mole. This gives 1.31 times 10 to the 6 joules per mole, or 1312 kilojoules per mole. So the first ionization energy of hydrogen is approximately 1312 kilojoules per mole. The key idea is that ionization energy shows how strongly electrons are attracted to the nucleus. It also provides evidence for electron shells, sublevels, and the structure of atoms.